Hello friends, I welcome you in lecture number 37 on relations. In this lecture also we will discuss one more question on equivalence relation and equivalence classes which was asked in GTU Winter 2022 exam. The question is define partition of a set. We have already seen the definition of partition of a set in earlier lectures in this lecture series on relations. Let capital A is the set having first 5 natural numbers and R is the relation on this set A, that is R is subset of A cross A, and it is given that R is an equivalence relation on this set A. We have to determine the partition for inverse relation. R inverse is the notation for converse of R or inverse of R, and we have seen the definition of R inverse. It is the set of all those ordered pairs AB for which BA is in R. In fact, we can obtain R inverse from relation R by interchanging the order of components in each ordered pair. So if BA belongs to R, then AB belongs to R inverse, or if AB belongs to R inverse, then I should write BA belongs to, if AB belongs to R, then BA belongs to R inverse. And here it is given that R is an equivalence relation, and we have to determine the partition for R inverse if it is an equivalence relation. If R inverse is an equivalence relation, then we are asked to determine the partition for R inverse, partition of this set A corresponding to R inverse. Now if you recall, in lecture number 36 on relations, we have proved that if R is an equivalence relation on a set A, then R inverse is also an equivalence relation on the same set. Therefore we can talk about partition corresponding to R inverse also. And here first we can write down the inverse of given relation R simply by interchanging the order of components in each ordered pair present in this relation. First order pair is 1, 2. 1, 2 belongs to R, therefore 2, 1 belongs to R inverse. For 1, 1 we will get this same order pair if we interchange the components. Here 2, 1, so we write 1, 2 in R inverse. 2, 2 belongs to R, therefore 2, 2 belongs to R inverse. Then 3, 3 all are diagonal elements. So if we change the order of components, we will obtain the same pair because these two are equal. This is the inverse relation for given relation R. And if you observe that this is exactly equal to given relation R, we can verify that 2, 1 is in R inverse. So here I have 2, 1, then 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 2, 2, 3, 3, 4, 4, 5, 5, and 1, 2. So by interchanging the order of components in each ordered pair of R, we obtain the inverse of relation R, and that turns out to be R itself. So here we have to determine the partition for R inverse, but R inverse is nothing but relation R itself. So either we determine the partition for R inverse or R, it is same thing because here R inverse turns out to be relation R itself, or inverse of R is R itself. Now to determine the partition, we have to decide the equivalence class for each element of given set A. There are 1, 2, 3, 4 and 5 elements here. So we will decide the disjoint equivalence classes corresponding to each element. And we know that if we have two elements related, suppose X is related to Y or ordered pair XY belongs to R, then we know that equivalence classes of X and Y are always equal. So here also we can observe that here order pair 1, 2, belongs to R. This implies equivalence classes of 1 and 2 must be same, and another ordered pairs are 1 1 2 2 3 3 4 4 5 5. So equivalence classes of 3 4 and 5 will be different, and the equivalence classes of 1 and 2 will be same because 1 is related to 2. So first we find out equivalence class of 1 by the definition. Equivalence class of 1 equal to all those elements in R inverse such that ordered pair 1 comma y belongs to R inverse. So I have to decide all those elements y which are related to 1. This I can rewrite in this way also. Y belongs to R inverse such that 1 is related to y by the relation inverse of R. So now I can observe here I have to concentrate on those ordered pairs whose first component is 1. So this is one possible ordered pair and this is another possible ordered pair. We can see that 1 1 belongs to R inverse. That means 1 is related to 1 itself. So 1 is the relative of itself. Then 1 2 belongs to R inverse. That is 2 is also related to 1. So there are only 2 relatives of 1. Therefore equivalence class of 1 has 2 elements, and this is nothing but equivalence class of 2 also because 1 and 2 are related to each other. 1 2 belongs to R inverse, or you can see 2 1 belongs to R inverse. Now we have to decide equivalence class for 3. So again by definition I have to decide all those. Here I have made a mistake. Here y is in a given set A. I have to decide those elements from given set A which are related to 1 here, and here they are related to 3. 3y belongs to R inverse. So we should take care of all these little things that we should not make a mistake. Equivalence classes are nothing but subsets of a given set. We are considering all those elements from given set A which are relatives of 1. Here also we are considering all those elements from given set A which are related to 3. Now I will concentrate on those ordered pairs whose first component is 3. So I have only one ordered pair whose first component is 3. 3 3 belongs to R inverse, that is 3 is related to itself, or relative of 3 is only 3. Therefore I have only one element in this equivalence class. Then I find out equivalence class of 4. So again by definition I have to collect all those elements of given set A which are related to 4, that is 4y belongs to R inverse, and I have to concentrate on those ordered pairs having first component as 4, and here also there is only one ordered pair 4 comma 4, that is 4 is related to 4. Therefore there is only one relative of 4 also. Equivalence class generated by 4 is also set having only one element 4 itself. Then equivalence class of 5, so that is nothing but all those elements in a given set which are relatives of 5. 5y belongs to R inverse, so I have to concentrate on that ordered pair whose first component is 5, that is 5 is related to 5. Therefore there is only one element in this equivalence class also, and we can see all these sets or all these equivalence classes are disjoint. All these classes are subsets of A. If we take their union, then we will obtain A. So now here we can write that this union of all these equivalence classes 1 3 equivalence class generated by 4, equivalence class generated by 5. If we take the union of all these sets, we will obtain given set A, and all these sets are disjoint or mutually disjoint. We can write that all these equivalence classes 1, 3, 4 and 5 are mutually disjoint. If we take the intersection of any two equivalence classes, then their intersection is empty. Therefore, they are mutually disjoint, and they are subsets of given set A. So therefore, we can write that this collection of all these equivalence classes 1, 3, 4 and 5, this collection is a partition of given set A, partition of set A corresponding to relation R inverse, corresponding to R inverse, and this is the answer to the given question. We had to decide the partition corresponding to R inverse if it is an equivalence relation, and here R is an equivalence relation. R inverse turns out to be R, therefore R inverse is also an equivalence relation, and using the definition of equivalence class, we are easily able to decide the equivalence classes corresponding to each element, and we obtain 4 disjoint equivalence classes, and their union is given set A. Therefore, this collection of these equivalence classes is a partition of given set A corresponding to R inverse. So this is a very nice question, and I stop here. Thanks for watching.